Hi, welcome back. So in today's video, we will learn about Prim's algorithm. It is an algorithm used to find out a MST. So let's see the outline of this video. First, we will get to know about what is the Prim's algorithm and how the Prim algorithm works, its pseudocode, running time, and finally the correctness of it. So let's see what is the Prim's algorithm. It is an algorithm used to find the minimum spanning tree. I have taught minimum spanning tree in the previous lecture, so if you don't have any idea, please look into it. And it is a greedy algorithm. Remember that Kruskal algorithm, which was taught in the previous video, was also a greedy algorithm. So now let's see how Prim's algorithm works using this graph. In order to run the Prim's algorithm, I am defining two set X, which are the set of vertices which will be included in the MST, and set V minus X, which is the set of vertices except the vertices in X. This Boolean array is helping me to do so. I will mark the vertices present in the MST as true and those who are not present in the MST as false. Prim's algorithm works in such a way that it finds the minimum edge between the set X and V minus X. And this result array will store the edge which is present in the MST. First of all, I am choosing A as the root node, so I will mark A as true. That is, it is included in the set X. Now, V minus X will have B, C, and D. As I have told that it finds the minimum edge between the set X and V minus X. The edges which is connected the set X and V minus X are 1, 4, and 3. The minimum of which is 1. So, I will increase the set X and add B to it. Now, I will mark B as true, add the edge 1 to the result array. Now set X will be these two, which contains A and B, and set V minus X will be D comma C. So connecting those two sets are 2 and 4. Minimum of which is 2. So I will add 2 to the result array and will mark C as true. Now similarly, the set X will be A, B, and C, and set V minus X will only be D. So edges 4, 5 are the ones which are connecting X and V minus X, minimum of which is 4. I will mark D as true. Now add 4 to the result array. As the size of the result array has become V minus 1, which is 3, the algorithm will end. We can see that it has satisfied both the properties of spanning tree, which is it is acyclic as a graph has 4 vertices which are A, B, C, and D, and the edges between them is also minimum, which is 1, 2, and 4. And the cost of the spanning tree is 7, which is obtained by adding all the weights of the edge. It can be seen that it is minimum among all the spanning tree. Hence, from performing the Prim's algorithm, we have obtained this minimum spanning tree. So before moving on to the Prim's algorithm, I am declaring some of the variables, which is a contain array. It is a Boolean array, which have been explained in the previous slide, that it checks whether the vertex S is selected in the MST or not. Array list result to store the edges which are included in the MST, and a heap to extract the minimum edge between the set X and V minus X. Moving on to the pseudocode. So I am inserting the source vertex as S. I am adding it to the set X by making the contain of S to true, and then making a min heap which contains all the edges from S to any vertex V, and this while loop will run till the size of the result array list is less than V minus 1. So let us assume that EI was the edge which was obtained from extract min, and its endpoints are UI and VI, and we are assuming that UI belongs to set X. So first we have to check that if VI is in set X or not. If it is not, we have to add it to the set X, add the edge which was obtained from the extract min to the result array, and add all the edges from VI to any vertex W to the heap. So this was the pseudocode. Now let us see the running time. We know edge can be added to the heap at most 2e times in the case of undirected graph from both of its endpoints. So therefore there will be 2e insertion and 2e deletion operation on the heap, and we know that heap operation take log time. Therefore the total time taken for the operation of heap will be log 4e times, which can also be written as log e times, and the while loops we run for e times, which is v minus 1. So the total time will be e log e, and we know the fact that e is less than equal to v square. Replacing e as v square, we obtain 2e log v, which is approximately equal to e log v. So let us see the correctness of the Prim's algorithm through some claims. Claim 1 is that Prim's algorithm will give a graph which is spanning. That is, it has included all the vertices and they are connected with each other. So I will prove this claim using induction. Before moving into the proof, we have given that the graph is already connected. So for n is equal to 2, which is the number of vertices, starting from a source vertex, I am including it in the set x, and the other vertex will be v minus x. And we know that the graph is already connected. There must be an edge between the set v and v minus x, so our algorithm will choose the minimum edge between the two vertices, therefore connecting them. The induction hypothesis says that for vertices equal to n, the tree will be connected. I will prove it for n plus 1. As n vertices were connected and belonging to the same set x, and the remaining will be a v minus x. Therefore, the Prim's algorithm again will choose an edge between set x and v minus x and will connect the vertices. Therefore, all the n plus 1 vertices will be connected. Moving on to the second claim, which is edge joining the set x and v minus x will be of minimum weight. So let's see its proof. So if I consider an optimal solution which pick an edge beta, which is not the cheapest edge between the set x and v minus x, and add this to the spanning tree T. Now if I consider the cheapest edge, say alpha, which is possible joining the set x and v minus x, so if I remove beta and add alpha, the cost will not increase and the tree will still be spanning and acyclic. Therefore, it is necessary that edge alpha, which is the cheapest edge connecting x and v minus x, should be included in the MST. So therefore, the claims explained say that the graph is connected, and for every set of vertices x and v minus x, the edge between them will have the cheapest weight. So which proves that for any pair of vertices there will be cheapest edge which can connect them, and as it is spanning, the result will be the MST. So let us see what we have got for you in the next video. I will teach you the Dijkstra algorithm, which is used for finding the shortest path. So that's it for today's video. Thank you.